or something like that. I'll have the equations on the back. So remember, there wasn't lots of plug and chug, right? And so anything that you need to understand the test will probably be on there. So, yes?
You said that we have to bring our own periodic table?
Yes. Yeah, for people who want, I'll put one up on the screen, but then everyone's looking up and down, and that's not good during an exam. So, but if people forget to bring their own, I'll put it on the screen. Yeah.
There's a lot of different versions of periodic tables, so does it matter like what it has on it?
Don't have it with too much writing. It will just confuse you. You know, if you need electronegativities or if you need valences, you know, those will probably be on the exam. So I won't ask you, I won't ask you anything that you can't solve without thinking about it, you know. And you should know the general trend, right? In electronegativity, you know, you don't need a periodic table to know that fluorine is more electronegative than carbon, or that lithium is more electronegative than potassium, right? You know, bringing a highly detailed periodic table will not get you a higher grade on the exam, I can guarantee it. Thinking will get you a higher grade, for sure. So that's why, you know, I don't want you to spend lots of time copying and reducing your study sheets or anything like that. I mean, you could, you know, I could give you the whole note set if you wanted to do the exam, and you'd get virtually the same grade. I guarantee it. I'm stressing thinking. So the things that you want to put on your note set are reminders, right? Polarizability is related to permittivity like this. This is why the dielectric permittivity decreases as a function of frequency. We know it does, right? We know this chart. So we know as frequency increases, dielectric polarizability goes down, right? And we know that this could be alpha or this could be KD, something like that. But we really want to know why we take these steps down. So, and that's a good thing to think about, right? Because you have, well, let's just say dipole oscillations, and these happen at 10 to the 7th frequency. And here you have something like, let's just say atomic. What's the frequency for atomic? 10 to the 15. And so you access all molecular motions at low frequencies, and if the molecules respond in all sorts of different ways, that will push up the polarizability and the permittivity. Versus if your frequency is very high and you're only accessing the atomic motions and the dipoles are just sitting there because the dipoles oscillate at very low frequency, that's why the permittivity drops. Yeah?
Are we getting that chart on the test?
No. It's not an equation, right? So this is a good chart to put on your study sheet.
You can't print.
I'll give you an equation, you know, anything that you need, like an equation, electronegativity, it'll be on there. But a chart is an idea, right? It's a concept. You won't get the solubility chart either. Yes?
Is it true that do we get like a cheat sheet? Like
Yeah.
Oh, I didn't know that.
Read the syllabus. Yes?
Did you say it was allowed to be
How
double-sided?
big?
Double-sided, 8.5 by 11, not machine reproduced, so it has to all be handwritten. Double-sided, 8.5 by 11. Yes?
Could you repeat that about the motion of it at high frequency?
Oh, sure. Okay. So here at low frequency, I heard you, Jawahar, 1 sec.
Same question.
Okay, yeah. So at very low frequency, so this is low frequency. And we have the different motions down here, right? We have dipole motion, we have atomic motion, we have 10 to the 16th, this is electronic. So at low frequency, we can access all of these things. So at 10 to the 2, if we're oscillating our field at 10 to the 2, everything else is moving, right? We can access all these motions. And the dielectric permittivity is a measure of the response of the material to our incoming field. And so if our incoming field is coming in at 10 to the 2 frequency, everything can move at that time scale, right? Electrons can move at that time scale, atoms can move at that time scale, dipoles can move at that time scale. So we have a high permittivity, or high response. But as we go to higher frequency, say here, so we're oscillating our electric field at something like 10 to the 14th. All of a sudden the dipoles look like they're standing still at a frequency of 10 to the 14th, right? Because at 10 to the 14, this thing moves 10 to the 7 times before this moves once. So remember, this is orders of magnitude difference in frequency. So this thing oscillates 10 to the 7th times before this thing goes through one oscillation. And so because of this high frequency, we don't access this dipole motion anymore. So we don't have the response of the dipole as part of our permittivity. So as we go to higher frequencies, different responses of the molecule drop out because they're moving so slowly, and the permittivity goes down.
I thought here, like, for the atomic motion, like, it should be like a specific frequency. So, like, I list that frequency that they will not have like atomic motion. Is that right? Like, each type of vibration has its specific frequency.
Yeah. So when you look into the details, right, you have these little peaks, and these are for UV vis. UV vis is an electronic, and these little peaks are in FTIR. So those things aren't shown on this big graph, right? So those little peaks are just small absorbances right along this line. But if you go to much lower frequency, this chart holds. And remember, those peaks are these peaks. Actually, they're the absorbance peaks, right? Because we have E double prime versus E prime. The real part of the dielectric permittivity and the imaginary part of the absorbance part. So UV vis and IR are these absorbances, right? Because we studied FTIR absorbance, UV vis absorbance. And they have a funny looking real response in the chart. It's some sort of delta. So know the general trend of this line. That's very important. And then, of course, for the absorbances, they go right on where the dielectric permittivity comes down because you see this absorbance of this motion. I saw a hand. Where?
Yeah, well,
Yeah.
the absorbance peaks are where like those interactions start happening, like the atomic and electronic. At those peaks are.
Yeah, these absorbance peaks are characteristic of a given dipole process. So one molecule might have a dipole that oscillates at 1 times 10 to the 7th. Another one might be 1.1 times 10 to the 7th. Another one might be 1.3 times 10 to the 7th. Same with FTIR, right? One oscillates at 1,000 wave numbers. Another specific bond oscillates at 2,000 wave numbers. Those are just very small pieces of this frequency axis. Remember, this thing goes from 10 to the 2 to 10 to the 17th. That's orders and orders of magnitude in frequency. An FTIR spectrum or a UV vis spectrum covers less than an order of magnitude in frequency, right? So it's a very, very small piece of this. So don't get confused just because we draw, so there's this plot, right, which gives you the big picture of dielectric response and frequency versus something like a UV vis where you have absorbance and you have a peak. So lambda equals 300. Here's lambda equals 200. Lambda equals 600. Right? If you turn this into a frequency, it'll be in the 10 to the 16th or 10 to the 17th frequency, right? But this is a really small chunk of this plot. And so there's just a couple peaks in there corresponding to the blow up of this spectrum. Yeah?
So we use the UV vis graphs to fingerprint like specific materials, right? The
Ye-
absorbance peaks.
Yeah, so either UV-Vis or FTIR, right? So if we have different wave numbers right here, so we have different peaks. So remember, UV-Vis is electronic transitions. FTIR is vibrational. Bonds, right, where we can tell the difference between C and H, C and C, C, double bond O. Here we look at electronic transitions. So we look at the transition between electrons going from one state to another state. And so that's a little bit different, where now we have highest occupied molecular orbital, lowest unoccupied molecular orbital, and we're looking at electronic transitions in these things. So you can still fingerprint stuff with UV-Vis. It's just more handy to fingerprint stuff with FTIR because the vibrational peaks correspond to exact functional groups. In UV-Vis, it's not like a peak at 300 corresponds to a CH bond, or a peak at 400 corresponds to a CO bond. It's a little bit more complicated than that. So we just talk about general shifts in UV-Vis or where things absorb, and FTIR we use for fingerprinting. And you got a taste of that on the homework, right? Even though benzene and aniline have different UV-Vis signatures, we didn't say that benzene has CH bonds, and so it's got a peak here in the UV-Vis, but it does in the FTIR when you fingerprinted your compounds. Does everyone understand that difference? Think about it. You can ask questions tomorrow.
Could you read that one more time? Just
Oh. Yeah, so FTIR gives us fingerprint of different bonds, right? Carbonyls, CH bonds, CN bonds, CO bonds. And so when you did the homework assignment for FTIR, you said, this peak corresponds to